Welcome back. So we're going to take a look at recursive functions again and do a little more with them. And our focus here is going to be on Fibonacci sequences. If you're not familiar with what they are, I'm going to show you. Fibonacci sequence is a series of numbers that look like this. Or you might see it written as, oops, you might have a 0 in the front. There we go. Something like that. Both are okay. Both are fine. We'll use the one with the 0 in front, I think, for this one. But basically, if we have the either sequence, right, we see a pattern here that emerges. And if you're not familiar with the Fibonacci sequence, it's a pretty common mathematical sequence. Wikipedia defines it as in mathematics, the Fibonacci numbers are numbers in the following sequence, and the thing that they have in common is that every number after the first two is the sum of the previous two. So we see here that 2 is a sum of 1 and 1. That's why I put a 0 here. We can see that basically after the first two, right? So 1 is equal to the sum of 0 and 1. 2 is equal to the sum of 1 and 1. 3 is equal to the sum of 2 and 1. 3 or 5 is 3 and 2. 8. So this sequence of numbers continues on. If you start at 0, right, and continue on, this sequence of numbers is also called the golden ratio. And the golden ratio is something that appears a lot in nature, right? So the Fibonacci sequence is something that is found in patterns of like seeds and curves of waves, spirals of snail shells, pine cones, branches of trees. I think even clusters of the universe are organized in the Fibonacci sequence, or a pattern can be found there. So, but generating these numbers there's nothing in JavaScript that you can just type in and say Fibonacci and it will get it for you. Okay, so how can we generate these numbers? Well, I'll show you the way we might do it mathematically, right? So we'll do the call a Fib equation. The Fib equation is simply given a number. The comments here. Fibonacci of a number equals Fib of a number is n minus 1 plus n minus 2. So we see there that given an input of n, we take that number, say 5. It wouldn't actually be the number itself. So 5 minus 1 obviously is 4, right? And then 5 minus 2 is 3. But it's actually saying that, not actually the numbers, but the Fibonacci 5 is not saying what, Fibonacci of 5 itself, because what if you did Fibonacci 6, right? There is no 6 in the Fibonacci sequence. So any number you put in here, say 5, is referring to the 5th place. And so then we take the 4th place and the 3rd place and add those two together. So we can see it here. So 0, 1, 2, 3, 4, 5. Okay, this is the 5th place. So what it's saying is that basically what is the 5th index position of the Fibonacci sequence, what is that equal to? And so we take the 5th position minus 1, that's 3. And then the 5th position minus 2 is 2. So we add those two together and we get 5. Shown another way, we can do it again. Fib 8, okay, actually no, Fib 6, okay, would be the 6th position. So 0, 1, 2, 3, 4, 5, 6. Okay, so we should get 8. Is going to equal the 6th position minus 1 plus the 6th position minus 2. So that would be 5. 6th position minus 1 is the 5th position, essentially. And this is the 4th position. So we see 5 plus 3 equals 8. So yeah, that's right. It's not actually the numbers adding up. The like 5 minus 1 is 4, but it's the actual position of the previous two numbers. So that makes it even more complicated, because it's not like you can just do Fibonacci, of 6 and say, oh, that's easy. That's, 5 and 4. But it's referring to the position inside the sequence. So you'd have to you'd have to generate those sequence of numbers, okay, in order to be able to get the, or if you said Fibonacci, the sixth, if you wanted to know what the, the whatever nth number is in the sequence, this is the equation you'd use to figure that out. Okay, so this is going to be like almost like a searching equation to tell you what is that number in that position. Or we can use it, as we're going to see, to generate all the numbers in the sequence itself. Okay, so in looking at this, let's take a look how we might want to do this in Fib in a loop. So we can see how we can actually program this inside of a loop. We call it Fib loop, and we'll take it a number n. And okay, so let's do let a equal 0, let b equal 1. And remember our first two, right? That's part of the equation itself, is that skipping the first two, every number after that is going to be added to it. So we're going to set those two up. And then we'll set up a temporary one. That's fine. Or actually we do val. Actually, we'll do temp. Nothing harder than naming variables in programming, right? Okay, so we have our first two positions, and then we have our temporary placeholder that's going to be used to calculate the next position. So, okay, if we're going to use a loop, let's do a for loop. Let I equal, we could set it at 2, right? Because we already have the first two there. And we could do I is less than or equal to num. I plus equal 1. Okay. And then for the body of the actual loop, let's do temp is going to equal, so this would be like the actual, like writing this out, would equal a plus b. So here we can actually see, okay, temp is right now this third position. So it'd be a plus b, so 0 plus 1, right? That's our first two. Okay. And then once we have temp assigned, we can reassign A and B. A equals B. So essentially we're going to shift these pairings over 1 every time the loop runs. So first time it's going to add up these two, and then it's going to add up these two, and then those two, and then those two. And we can do that simply by just swapping the values as it goes, shifting one over, and then giving the new values to the ones that were previously there. So B equals temp. And then we can return temp. So we make the fib loop equal to temp. Okay, and then it will guess the value at the end. We can console log. And let's find out what's in the same as above. We can do the let's do the 6th position. Let's see what it comes up with. Okay, actually, we're getting our previous one up here, so I'm gonna comment that line out there. The factorial. There we go. Okay, 8. So in the 6th position of the loop, we see 8. And how did we get there? Every time this runs, let A equal 0, let B equal 1, let temp equal 1. Every time we just run the loop, we add the A and B, and then we change what A and B are. A moves over 1, so A was previously 0. We move over to 1. B gets the new sum of the two pairings, so that would be, in this case, 1. And then the for loop runs again. So temp, remember, assignments happen right to left, so it's going to do this calculation first, and then assign it to temp, right? So it's going to calculate the new A and B, which would be 1 and 1, and then that's going to get assigned to temp, so temp's going to equal 2. A is going to get B, so this is going to move over 1, and then B is going to get temp, which is 2. And then it runs again. Temp is going to get the next two, which is going to be, let's see what we're on. We're on 3, I think. So temp's going to get 1 and 2. No, actually, it's 5, right? Temp's going to get 5, which is 2 and 3. And then so on and so on, however many times we want this to run. Okay. So why did we start at let I equal 2 instead of 1? Like we might usually do? Okay, we can see that because we are already doing a calculation for the loop here, and we already have 1 and we're adding 1 to it, Basically, it's going to give you the one additional position because we basically are starting back over and counting that 1 twice. So we do 2 so that it actually starts with 1 fewer number, I guess. You could actually do while I is maybe less than num and start at 1. We could do that too as well. That would solve that problem. Let's see. Yeah, it gives us 8. So it all depends on what you want to do. Either one will work. So either 2 and equal to num, less than equal to num. Okay, so that's our loop there. That's the first iteration of it. All right. Now, how can we rewrite this? Our purpose is to take a look how we could rewrite this as in recursion, as a recursive function. Function fib recur num. We'll take it in num just the same. We have to have, what do we have to have? We have to have our exit condition, base condition, and recursion. Okay, so we'll set up a base condition. If we'll do, what's the worst case scenario? Well, you know, there are ways mathematically to figure out Fibonacci sequences if there's a negative number here, but we can just do if num is less than 0, return undefined, else if num is equal to, let's say 0. Yeah, because that doesn't make sense, right? It would do, actually, if num is less than 2, right? Because 1 or 2 is the first 2 numbers we don't need. We can just do return num. We'll just give back that same number again. If they enter 0, we'll just give them back 0. If they enter 1, we'll give them back 1. There's nothing to add up, right? And then the last one is else. Then we run our recursion. So, all right, so labeling this, we have our exit condition. We have our base condition. And then we have our recursion. Else. And for the else, what we can do is let's return fib recur num minus 1 plus fib recur num minus 2. Okay. So what do we have here? This is probably seems rather confusing, but what we have here is our function that goes through and checks. If they enter, say, they want to know what the position is of, say, above, we'll do the same thing. Say the 6th position, right? So the 6th position, it checks. Is it below 0? No, it's not. Is it less than 2? No, it's not. Okay, so then what's it going to do? It's going to return the sum. So that's the first thing this Fibonacci recursion function is going to be equal to, is the sum of n or 6 minus 1 plus 6 minus 2, or num minus 2 in this case. Okay, so then that gives us the initial position. Now, well, let's just say, just out of curiosity, why couldn't you just do num, right? Num minus 1, num minus 2. Something like that. Well, we did that, let's see, kind of up here, I guess. Yeah, because we assigned the variables A and B. But this doesn't necessarily work because it's not getting the number. If we run this, I'm going to console log that out. Okay, we should be getting 8 back. Oh, we're going to actually run it. Console.log fib recur 6. Gives us back 9. So why does it give us back 9? Well, num minus 1, 6 is 5. Num minus 2 is 4. So that gives us 5 plus 4 is 9. Right? That's not what we want. So what can we do? We ran a for loop on here, okay, that essentially is going to swap over the numbers every time it runs. So we could do the same thing here by, instead of doing the -1, we can return the Fibonacci Fib recur. Fib recur of num minus 1 and num minus 2. Okay. And let's just take a look here. I'm going to get rid of this sum here to show you what exactly is Fib recur num minus 1 inside of Fib recur num 6. Okay, it's 1. Why is it 1? So let's take a look at what's happening here. So it goes in there and it's going to basically reduce that number or go through that number a number of times, right? Because it's going to keep on calling itself till eventually, num minus 1, eventually it gets down to this number here. And eventually, when it takes the num, so 6 minus 1, so we essentially call Fib recur again, except this time when we call it with 5, right? We eventually entered 6. This is going to be 6 minus 1, so that's 5, right? Essentially, we're calling it, Fib recur 5, run that again. Okay, and eventually, when it runs, it's going to keep on minusing it, right? Because we did num minus 1. It's going to minus it until it gets to 1. And at 1, it's going to trigger our base condition. If num is less than 2, return that number, which is going to be 1. So we don't want to do that. We simply want to return that value, okay, of that number. And then we want to go and add it to Fib recur num minus 2. Okay. So we add those two numbers together. So this is never going to drop down to 1 because the number, the return value of the sum of these two, okay, is always going to be positive because we skip the first number, right? It will be, first time this runs, it will be 0 and 1, and then 1 and 2, right? It's always going to go positive at that point. So you're never going to be minusing it to drop down to one of these exit or base conditions. We just add those just in case. Like if we typed in here, like negative 10, when we ran it, we see that the number is below 0, return undefined, right? Because our program can't handle negative numbers right now. Like it handles 6, it returns the proper value for that. Okay. So what is this doing? How is it working, right? So we can take a look at that in just a second, and we can take a look at what's happening, let's say, behind the scenes for a Fibonacci recur of, say, the number 5. And I'll do it all out for you so you can see. It's going to reduce everything essentially to 1 and then add it all up. So basically every time we run this program, it's going to result in 2 new groupings coming out and 2 new values. And eventually we're going to get smaller and smaller until the numbers ultimately, this program is going to reduce everything to either a 1 or a 0 and then add it all up. And I'll show you how or why it does that. So Fib recur 4 and 3. Okay, and then we pass those through and say it becomes 2 new branches. So Fib recur 4 is going to then become Fib recur. This is the first time it runs. Second time will result in these splitting. So then we'll get out of 4, we'll get 3 and 2, right? Because minus 1, minus 2. Plus Fib recur minus, 2. There we go, so minus 2 equals 2. I'll wrap those in parentheses. That was 4. Plus the result of Fib recur 3. So out of the 3, we get 2. Plus Fib recur 1. Okay. That's the next time it runs through. All right. And then the third time is going to result in those numbers splitting again. So 3 then becomes 2 and 1. I actually have it here, 2 and 1. Okay, so the 3 becomes 2 and 1. And then we also have 2, right? and 2 becomes 1 and 0. All right. And then, so that's just 3 and 2. And then we're adding that to the result of 2 and 1. So once we get down to either a 1 or a 0, the program effectively stops working. So this fib recur 1 at the end here is essentially the end of the line for that one, because we said if the number is less than 2, if it's less than 0, undefined, but if it's less than 2, we would just return that number. So once it gets either to a 1 or a 0, it just stays that way. Okay, so then we can just add in to the end of that line the fib recur that was up here. So we're essentially going to drop down any 0s or 1s that we occur, because they're just going to stay that way anyways. So we see a lot of 1s and 0s here. We're just going to keep those there. But now we got to split up that 2, right? Fib recur 2 is going to split into 0 or 1 behind the scenes. Okay. So this is the, let's see, second, first, oh, wait, that's supposed to be third. Third, and then the fourth time it runs through, we're going to see that where the 2 has now been split into 1 and 0, and then I just drop down everything else that's going to come along for the ride. Okay, and so then, yeah, so whatever the number is, 0 or 1, that's going to stay that way. So in this case, this is the same thing as saying 1 plus 0 plus 1 plus 1 plus 0 plus 1 plus 0 plus 1. Okay, so the original question was, what is the number at the 5th index position of the Fibonacci sequence? And if we add all these up, right, 1 plus 1 plus 1 plus 1 plus 1 is 5. We look it back up at here, and at the, get rid of that one for right now. At the, starting at 0, at the 5th index position, 1, 0, 1, 2, 3, 4, 5, we see 5 as that value. So I don't expect you to be able to know this logic. You know, if you're following along, that's good enough. But basically showing you how we can take, and actually we can clean up this function a bit here too, because we actually have, if number is less than 0, if number is less than 2, it's not going to go below 0, because by the time we get to 2, it's going to stop. So we can actually clarify this to be, if it's below 0, we can actually just say return num. And actually, that makes it even cleaner. So yeah, we can just rewrite fib recur into essentially 3 lines of code. If num is less than 2, return num. Otherwise, return a recurring version of itself. And we look at this up here, where we're reassigning variables. This is a lot more challenging to figure out what's going on. I mean, I know this is challenging to figure out what's going on, but to read the code, it's harder to figure out or trace variables here than it is down here, where if you can imagine this happening abstractly, this is a much easier way to imagine the Fibonacci sequence and finding out those numbers at those index positions. And I did this out just to show you that what's happening behind the scenes is fairly simple, but it's hard to imagine when you're trying to write this out. So, but just an example of a function calling itself to figure out a mathematical equation that would be hard to do inside of a loop, or confusing to do inside of a loop, as we saw up here. Now, all right, so mathematically, I mean, you can do this to, there's all sorts of different math equations that the more you get into computer science, the more they're going to be explained. The math behind it, I just did this as a simple, or not simple, but, you know, as an example of using recursion for a math problem. But there's a lot of math behind the scenes here to figure out mathematically how to structure an equation or how to structure a program to do this, and it takes a bit of practice to get used to doing it. In real, you know, all right, so math is one place, but, you know, what about if you're in web development? What are recurring functions there? And yes, so obviously you're not drawing a lot of golden ratios in web development, but web development has its own challenges in that beyond math there's a purpose for it, in that when you write your callback functions, if you did a callback function inside of a loop, meaning that callback function, maybe that callback function job is to go to a server and get some information and retrieve it back to the website. or retrieve any information from a database. It could be designing a game in a game engine, and you have to confront this problem. That function, if you run in a loop, the loop is going to say, okay, go get this information, and then it's going to move to the next item in that loop. It's not going to wait for that information to come back. So you'll see a lot of recursion with callback functions to wait for that information to resolve, waiting for that function to resolve to retrieve that information before the program progresses. You don't want the program or the website to continue loading information if it's wrong, if it's incorrect, or run the next bit of information or calculations if the information coming back from the server is delayed for any point. Right? We all know that working on the internet, the connection, things don't always happen instantaneously, right? It can take some time. So a recursive function in web development is going to make sure that the function won't call itself again until the processes are executed with the proper or the correct inputs. So recursion is not just something that you see just in math, even though there's a lot of it out there with math. You're going to see a lot in actual practical applications as well too, like I said, with web development and other programming types. So I wanted to show you it. It's an important part of computer science, important part of programming, to at least not be able to maybe draft it right off the bat, but at least know when you see it, what exactly is happening there. When you see return factorial, factorial is calling itself. That's like saying, what's the definition of being tired? Well, it's, being tired is in the state of being tired. And you're like, what does that make any sense? But here it does, because essentially it creates a loop that can change dynamically to whatever the conditions are inside of that function, or whatever the changing conditions are that function handles. So it's a pretty elegant way of writing it, but you can see it get kind of confusing here. And it can actually, as this goes, this is sometimes called a recursion tree, or recursion branches, where you'll have splits where everything will split into two, and then that will split into two, and that will split into two, and so on and so on. So the last question then, I guess, is that looking at this, because we're talking about calculation time, and we did a small number like 5, because this would have been really, really a lot to write out for like something like 50. But if we wanted to do something like 50, what will happen? Saying, oh, you know what it is? It's all this stuff. Let's comment that out, and I'll go back up here to the one I had and change that out for 50. Undefined. Why is that undefined? I know what I did wrong. If yeah, right here. There we go. Forgot to move the bracket up to under the return num. Okay, we see it calculating. Still calculating. All right, so we went from 5 or 6 to 50. Okay, still calculating. We can see, because it's going to be doing this branching for every number that it has. It's processing the factorial of that number down to 1. So, and it's doing it for every time it runs the function. So it's still calculating. This is going to take a long time for such a large number. And essentially what we're asking is, what is the value of the 50th position inside of a Fibonacci sequence? And so it has to calculate all the numbers up to that point to tell you what that is. You see it's still calculating. This is going to take some time depending on how fast the server CPUs are. Yeah, we're going to stop that one. Let's try 15, see what happens. Still going to take a while to calculate all this stuff. It's not, this is not what we call, cheap or inexpensive calculations, Fibonacci sequences, and we're going to get to calculation time and how to figure out calculation time in an upcoming video. But essentially we're figuring out a, almost a factorial of the Fibonacci sequence, right? Because we're factoring each one down and then factoring those two out, right? It's a fairly expensive calculation to run. And so we can see it here. Even at 15, this is going to take a long time to run. Let's try, how about 10? This is not on my computer. This is on their servers, so Still running. We calculated 6 and it, let's see, go back, make sure everything's still working. 6. Maybe we're being throttled now because of our calculation time. So yeah, it's something to consider. You know, the speed of your algorithms, the speed of your programs, even though it's 3 lines, we're asking you to do some pretty, comprehensive math here to figure out what those numbers are. Page unresponsive. Yeah, we've crashed the website. Yeah, Chrome is like, it's not working. Okay, so that's it for this video. We'll take a look at algorithm speed in a future video, and we'll figure out which one's faster. I think you have an idea of which one's going to be faster on this one. We'll go into why it's going to be faster. All right, thanks for watching. See you in the next one.